7.7 Group Trends for the Active Metals. Our discussion of atomic radius, ionization energy, electron affinity, and metallic character gives us some idea of the way the periodic table can be used to organize and remember facts. As we've seen, elements in a group possess general similarities. However, trends also exist as we move through a group. In this section, we will use the periodic table and our knowledge of electron configuration to examine the chemistry of alkali metals and the alkaline earth metals. Group 1A, the alkali metals. The alkali metals are soft metallic solids. All have characteristic metallic properties such as our silvery metallic luster, high thermal electrical conductivities. The name alkali comes from the Arabic word meaning ashes. Many compounds of sodium and potassium, two alkali metals, were isolated from wood ashes by early chemists. Sodium and potassium are relatively abundant in Earth's crust, in seawater, and in biological systems. We all have sodium ions in our bodies. However, ingesting too much sodium can raise our blood pressure. Potassium is also prevalent in our bodies. A 140-pound person contains 130 grams of potassium as potassium ions in intercellular fluids. Plants require potassium for growth and development. Some of the physical and chemical properties of the alkali metals are given in Table 7.4. The elements have low densities and melting points, and these properties vary in a fairly regular way with increasing atomic number. We can also see some of the usual trends as we move down the group, such as increasing atomic radius and decreasing first ionization energy. For each row of the periodic table, the alkali metal has the lowest first ionization energy value, which reflects the relative ease with which the outer s electrons can be removed. As a result, the alkali metals are very reactive, readily losing one electron to form ions carrying a positive 1 charge. The alkali metals exist in nature only as compounds. The metals combine directly with most nonmetals. For example, they react with hydrogen to form hydrides and with sulfur to form sulfides. The symbol M in equation 7, 17, and 18 represents any of the alkali metals. In hydrides, the alkali metals, lithium hydride, sodium hydride, so forth, hydrogen is present as an H negative, called a hydride ion. The hydride ion in which the hydrogen atom has gained an electron is distinct from the hydrogen ion, H+, formed when a hydrogen atom loses its electron. The alkali metals react vigorously with water, producing hydrogen gas in a solution of alkali metal hydroxide. These reactions are very exothermic, and in many cases, enough heat is generated to ignite the hydrogen, producing a fire or sometimes even an explosion. Figure 7.25. The alkali metals react vigorously with water. The reaction of lithium evidenced by the bubbling and escaping hydrogen gas. B. The reaction of sodium, more rapid and so exothermic that hydrogen gas produced burns in air. And C. Potassium reacts almost explosively. This reaction is most violent for the heavier members of the group, in keeping with their weaker hold of the single valence electron. The reactants between the alkali metal and oxygen are more complex. When oxygen reacts with metals, metal hydrides, which contain the O-2 ion, are usually formed. Indeed, lithium shows this reactivity. Lithium plus oxygen yields lithium oxide. When dissolved in water, lithium oxide and other soluble metal oxides react with water to form hydroxide ions to form the oxide ion with H2O. In contrast, the other alkali metals all react with oxygen to form metal peroxides, which contains the peroxide ion. For example, sodium forms sodium peroxide. Potassium, rubidium, and cesium also form compounds that contain the oxide ion, which we will call superoxide. For example, potassium forms potassium superoxide. You should be aware that the reactions shown in equations 7.21 and 22 are somewhat surprising. In most cases, the reaction of oxygen with a metal forms a metal oxide. As evidenced from equations 7.19 through 22, the alkali metals are extremely reactive towards water and oxygen. Because of this, the metals are usually stored submerged in liquid hydrocarbon, such as mineral oil or kerosene. Although alkali metal ions are colorless, each emits a characteristic color when placed in a flame. The ions are reduced to gaseous metal atoms in the central region of the flame. High temperature of the flame then excites the valence electrons to a higher energy orbital, causing the atom to be in an excited state. The atom then emits energy in the form of visible light as the electron falls back to the lower energy orbital and the atom returns to its ground state. Sodium, for instance, gives a yellow flame because of emission at 589 nanometers. This wavelength is produced when excited valence electron drops from the 3p subshell to the lower energy 3s subshell. The characteristic color emission of sodium is the basis for sodium vapor lamps. Group 2A, the alkaline earth metals. Like the alkali metals, the group 2A elements are all solids at room temperature and have a typical metallic properties, some of which are listed in Table 7.5. Compared with the alkali metals, the alkali earth metals are harder and more dense, and they melt at higher temperatures. The first ionization energies of the alkaline earth metals are low, but they are not as low as those of the alkali metals. Consequently, the alkaline earth metals are less reactive than their alkali metal neighbors. As we noted in section 7.4, the ease with which the elements lose electrons decreases as we move across the periodic table from left to right and increases as we move down a group. Thus, beryllium and magnesium, the lightest members of the alkaline earth metals, are the least reactive. The trend of increasing reactivity within a group is shown by the way alkaline earth metals behave in the presence of water. Beryllium does not react with water or steam, even when heated red hot. Magnesium reacts slowly with liquid water and even more readily with steam to form magnesium oxide and hydrogen. Calcium and the elements below it react readily with water at room temperature, although more slowly than an alkali metal adjacent to them in the periodic table, as shown in figure 729. The reaction between calcium and water, for example, is calcium plus water yields a calcium oxide and hydrogen gas. The reactions represented in equations 723 and 24 illustrate the dominant pattern of reactivity of the alkaline earth elements. They tend to lose their outer two s electrons and form 2 plus ions. For example, magnesium reacts with chlorine at room temperature to find magnesium chloride and burns with dazzling brilliance in the air to give magnesium oxide. In the presence of O2, magnesium metal is protected from many chemicals by a thin surface coating of water-soluble magnesium oxide. Thus, even the magnesium is high in the activity series can be incorporated into lightweight structural alloys used, for example, in automobile wheels. The heavier alkaline earth metals, calcium, strontium, barium, and even more reactive towards nonmetals than is magnesium. The heavier alkaline earth ions give off characteristic colors when strongly heated in a flame. The colored flame produced by calcium is brick red, that of strontium is crimson red, and that of barium is green. Strontium salts produce the brilliant red color in fireworks. The barium salts produce the green color. Both magnesium and calcium are essential for living organisms. Calcium is particularly important for growth and maintenance of the bones and teeth. In humans, 99% of the calcium is found in the skeletal system.